Alright, so welcome to my videos on calculus. And don't worry, calculus is not as scary as it might seem, although it seems like the end of the road for high school math. It's kind of the beginning of a new way of thinking about math. And the fact that you play with infinity, it'll make sense, don't worry. The fact that you play with infinity kind of makes it, I don't know, it's kind of like my favorite topic just because of all that you can do with calculus. And technically, all it means is the mathematics of change. So anything that changes, we kind of study it with this idea of calculus. Now, it still sounds freaky, but don't worry. Here, know what calculus means in Latin, or at least its original definition. Know what it means? You're not going to guess it, probably. It means pebble. And you think, well, I don't get it. Like, you're joking. No. So we'd count with pebbles, right? So we'd calculate with pebbles. So that's where the word calculate comes from. Calculus is just a fancy word for calculation. And that's kind of at the heart of calculus. I mean, doing the actual playing with infinity is it's actually in a way the easy part. The hard part is doing the algebra. And so it's kind of all about the calculation in the end. But it's pebble. So if anyone ever asks, what's calculus? That's really hard to understand. Well, are pebbles hard to understand? No. Well, actually, maybe like how they come to form, that's all difficult, but that's for another day. Let's keep going with this. So you've probably seen calculus symbols. Here's one. This is called the integral. And it doesn't have to be dx, it could be dt, dy, whatever. But it's called the integral symbol, and this is just known as a differential. Don't worry. Also infinitesimal if you want to think of it that way, but we'll all get into that. And also, you'll also see this, and this is called the derivative. In this case, it's a derivative of y, but again, we'll get into this stuff. So these are the two big concepts, and you'll see all sorts of variations. Sometimes you'll see like this, or sometimes you'll see a double integral, dx, then dy. Or maybe sometimes you'll see like a contour integral. All sorts of fancy things, and then you'll see like a c here, and then you'll also see like a to b, and stuff like that. It just gets wacky. And you'll also see it in all sorts of ways you didn't realize are the same thing. This, if you put two slashes marks, it actually is the same thing as this if y is f of x. Either way, don't worry about it. I'm just showing you what symbols you'll see that stem from calculus. So again, calculus means pebble. If you ever get stuck up in all this, just remember all you're doing is calculating. Go back to pebble. All right, and it's something to hold on to, so you don't, you don't get too bogged down in it. So so how should we start? I'm gonna start usually considered the bad way, which is starting with so by the way, there's integral, there's a derivative. So there's differential calculus. That involves the derivative. I'll tell you what that is probably next video or next set of videos. And then there's also integral calculus. Now we usually do one before the other. It's kind of like introducing multiplication and then introducing factoring or division. But in this case, we're going to start with the integral or integral calculus. So either way, yeah, people usually advise against this, but I think they both make sense on the surface. So I kind of want to do what sounds tricky first, just so we can get out of the way. So we're going to basically go into this first. So let's get started. So this is kind of the challenge I want to propose. I'm going to set up axes. All right, there's our x-axis and there's our y-axis. Again, this is called Cartesian coordinates, named after a guy named Descartes. Interesting guy who basically combine the concepts of algebra and geometry by graphing circles and such. Either way, that's just a side thing. By the way, I should have even told you. The ideas of calculus were by two great mathematicians. One would be Leibniz. I like that the Z is pronounced TZ here, but Leibniz. Either way. And then you also have Newton. Usually Newton gets credited for all this stuff, but they're kind of equal here. They came up with this stuff at about the same time, I believe, 1650s. And on this, so Newton was kind of looking at planets, and Leibniz, I forgot what he's doing, but he's kind of a math wizard, and who's already kind of, I don't know, I think he's just messing with math, and he came across this stuff. And they did this about the same time in the 1650s. So, either way, so this is kind of the question that they probably asked themselves. So we have these ways of graphing things, but, so here's the problem. I'm going to make 3 graphs. This will be our first graph. It's just a straight line. And so we'll say it's y equals, I don't know, y equals, let's say, a, yeah, just a. It's a constant number. Whatever x value you are at, it's always going to be a on the y-axis. So if you go to 5, still a. Go to -2, still a. So it's just this flat line. All right, now I'm also going to draw another line, and there's going to be a linear, and it's going to go through the origin, so I don't have to add anything to it. It's going to be, here, this will be our y1, this will be y2. This is going to be equal to b, we already used a, times x. So the further down on x, the higher this will be, because you're multiplying by a greater value of x. And b could be any constant. It's just that if you're at 1, it'll be a height of b. That's just how it is. And if you're -1, it's a height of -b. I guess you could call it height. Y direction, it's -b and positive b. And then the last function. This is going to be the hard one when I ask this question. And by the way, they won't intersect exactly like this. It all depends on these b and a values. And also one other value, which I'm introducing right here. And this will be, so this will be y3. And let's put the equal sign on this side just because we're running out of space there. Cx squared. So if you know a parabola, that's an x squared. And c could be anything. It could even be like negative numbers. A, b, and c were kind of innovated by Descartes, who came up with Cartesian coordinates. And they're just used always as constants. So we're going to do the same thing as them. Either way, so I drew these 3 graphs. What do I want from them? This is what I want. So I'm going to name 2 points. Let's change colors here. I'm going to call this one alpha, because we already used a and b's and stuff like that. And then this one beta. Beta after alpha. And so I'm curious, on each graph, what is the area from alpha to beta on each graph? So on this y1 graph, it's this whole area right here. On the, I'm going to change color so you can see it. On the y2 graph, it's this kind of trapezoidal area right here. And then on the hardest one here, good luck solving this one, is this curve right here. And everything's arbitrary here, so we can just shift it over our understanding of numbers. So it's not like, oh, now we can only solve this if it's 2x, because I have no idea others. Either way, just find the areas. And then I'm just going to make up a notation that I want you to use. So the area of, let's say, y1, that'll be the first one. And you're taking the area from alpha to beta, because you need a distance here. You can't just say area, just area outright. So we're going to go from this alpha to our beta, first point to last point. So I want you to find an equation that incorporates b and alpha. That should be easy for y1, but then do the same thing for y2, maybe a little more difficult. And then the last one, area for y3. All right, have at it. Um, I'm going to start working through one, and I'll work the same direction as I wrote these. So I'll do the first one, and try to do these ahead of me. Maybe pause them, just because some of them will be somewhat simple. The only hard part might be getting used to writing alpha and beta, just because that they look fancy, but it's just another thing for A and B that we haven't used already. So the first area would be this straight line. I'm just going to draw it all in the same color. And so there's two ways to think of this. One way is so B to A, and the height here is going to be A tall because it just stays A, and the height here is going to be A tall. So this is a rectangle, and to find the length of the rectangle, it's length, well, height, times width. And width here would be the distance between B and alpha. Beta and alpha, I mean. So that is, I think, our first formula. So right now is A beta minus alpha. And I'm going to write it one other way. You could have done this another way. You could have taken the area between 0 and beta. So that area. And then you could have, let's change colors here so you know what I'm talking about. Then you have this area here from 0 to alpha that you can calculate. And if you remove that from this black area, all you get left is the area you're searching for. So let's call it green. All right, so in this case, you'd have a length of beta. So A times beta minus an A times alpha, and gets you the same result. So you can find it by subtracting. Now this will help you in the long run, doing it this way. But you can see, if you just multiply in the A, you get this result as well. So this is the other result you can get. A times beta minus A times alpha. All right. It's getting a little scrunched up, but I kind of want to stay on this page. I think we can. Just try to follow along closely. All right, so next one we have a triangle. And there's two ways to do this. Yeah, we should switch pages. But it's a triangle, and the equation for it is, if I remember right, b times x. Just to check, b times x, b times x. So we want y2 here. Y2. So a of y2. So the area of y2 from alpha to beta. And this is totally a notation that I made up, just because I think it makes sense. You have an area to calculate here. All right, and let's see. So we have a triangle. So this is our line, and let's draw an axis. Luckily, it goes through the origin, so it makes lots of our math pretty simple here. And then this equation in purple, probably looks the same color here, is, so it's y2, and that's equal to b, not beta, times x. All right. So we're doing it from, let's change colors one more time. Let's do this orange. Alpha to beta. And really, these are so arbitrary that alpha could even be 0, or it could be negative. But the math works out all the same. You can check for yourself whether it was negative or positive. So we want this area. So one way is if you know your trapezoid formulas. So this is still a trapezoid, lots of people forget. But this is called a right trapezoid just because it has one right angle right here. I'm just turning on its side. And so the height here, right here, so this length is, in this case, it'd be alpha times b, because this is at point alpha on the x-axis. So alpha times, so let's put b first, b times alpha. And this distance here would be the similar, it'd just be b times beta, b beta. Let's change colors here. So the cool formula here is, and by the way, the height between them is beta. Here, let's change the colors. Is beta minus alpha. It's just this distance here. All right, and the cool formula here is it's let's call this base 1 and base 2. Let's do capital B because we haven't used capital B. So the cool formula here, let's call this H for height, is B1 plus B2. I recommend you try to prove this, but that's for another day. It's the average of the two bases. You could also call them heights in this case because they are kind of the heights. Well, multiplied by this height. So let's plug stuff in. So B1 in this case is, B1 is bottom. So B times beta. Oop, what am I doing? B times beta plus B times alpha. All divided by 2. And the height is beta minus alpha. Agreed? Yeah, I think so. And by the way, I'm going to show the other way. Honestly, this is just to show you a nice geometry trick you can do for this. And then I guess you could do some factoring in. Looks like you're going to get like a B. So everything's going to be divided by 2. I'm just going to leave it there. So, and by the way, all of this is multiplying into there. So either way, B beta squared plus B alpha beta. Sounds like a sorority or something. Alpha beta gamma. Then we have B beta. Sorry, sometimes I just get sidetracked. Times alpha, and last one is plus B beta. No, B alpha times B times beta. There we go. And this times beta, this times alpha squared. I multiplied times beta once. So the cool thing here is these two cancel out. Nice. And now we're left with a B beta squared. And let's just distribute the 2's. And this is supposed to be negative because we multiplied times a negative alpha. Thanks for checking, Quentin. And minus B alpha squared 2. All right. Now, it seems like we just wasted a lot of time here. The other way you could have solved this might seem too. This is based off of that first way we did for the flat one. Either way, so we have you could think of this as 2 triangles. This triangle here, this big triangle from alpha to beta. I mean 0 to beta. So the length here is just beta, that's nice. And the height here would be beta times b, beta b. And then you subtract that, this whole area, from the small area inside of it, from 0 to alpha. So just the length of alpha on bottom. Let's put an alpha there, beta here. And the height here would be alpha times b. All right, and so it's alpha b times alpha. And remember that this is base times height divided by 2. Base times height divided by 2. That's the triangle formula. And luckily this is already set up as right triangle. That's why Cartesian coordinates are so nice, just because you always have right triangles. And by the way, that whole unit I had on right triangles is for a reason, because you could analyze this with trigonometry too if you felt so inclined. But let's just keep going with it. So you have the length of alpha here, length of beta here. So beta times beta squared times b, and that's divided by 2 because it's a triangle. And you subtract that from that you subtract b alpha squared divided by 2. Check it out. We get the same result both ways. Seems like a waste of time, but I'm not going to write it up here. I'm going to write it on our main page. And I'm going to write it in this format. So what do we get? So honestly, just beta squared divided by 2 times b. And then alpha squared divided by 2 times b. So b times beta squared divided by 2 minus b times alpha squared divided by 2. All right, so we solved 2 of them. So now we know that any flat line, just using geometry, has an area from alpha to beta, any point. The area is gonna be on a flat line is just the a value times beta minus the a value times alpha. And these rules extend pretty well, but the hard one, which I recommend you try before I do the next video, is this one. What is the area under, let's draw right here. What is the area under here from alpha to beta? I completely recommend you try this. Maybe you could do like represent this with a triangle, see if that gets you anywhere. And so that's your challenge on the curve cx squared, and that's y3. So find the area of that. All right, thanks for watching so far. All right, so find the area of that, and then watch the next video. And if you fail, don't worry. I would normally fail at this, but there you might see a pattern happening with these values by this third time.